Okay, I've published a few work and sort of I've gone around the different fields, different domains of deep learning. I started using neural networks really early, before it was really working, before the term deep learning really came about. And then once on the deep learning era, I also worked on computer vision. There's a work that we proposed to improve convolution to be translation aware. And then lately, I've also worked on NLP. So it's sort of like sampling different flavors from different fields, kind of, as I said, non-traditional, but it's been really fun. I also run a weekly reading group where we read a paper a week. It's as simple as that. Actually, we don't even read it. I invite a speaker, usually the author of the paper, to come and talk to us about that paper, because I'm lazy. I don't sometimes say, that's like my method to keep up with the research. I invite someone to tell me what that paper is about. So feel free to join. The link is in the slides and on my website. I try to put it everywhere, so people who are interested in join can always join. It's free and open to the public. And I co-founded and am currently managing a nonprofit research org called ML Collective. Basically, we're trying to change the ways people become researchers, or at least providing an alternative people to become researchers. Like maybe you don't feel like going to grad school, but you're still interested in publishing research. We're providing a ways to do that. You can have a full-time job to support yourself, or if you feel, leaving your full-time job and focusing on just research full-time, you're able to do that. So all those alternate paths to become a researcher, we're supporting. And we're supporting you with mentorship, and everything's free. Cool. Let's get to today's content. Basically, we're talking about NLP, natural language processing. So what is natural language processing? Well, very plainly, it is the understanding of human languages, of course, using tools in computer science and machine learning. And interestingly, maybe if you're working on computer vision, you would think first few problems you would think about would be, image classification and object detection. So all those, what I call summarization problems, meaning you look at some data, you're trying to make meanings out of it by, summarize it into, say, a class, or some notions to describe this image, a concise notion. But interestingly, if you're working on language, you almost like the first problem you would start thinking is producing that language. Somehow, if you are studying language with machine, you would naturally think that, okay, I will be interested in training a machine to produce such language. Of course, in image tasks, you have such things. You have GANs, you have generators, you have generative modeling. But at least in my experience, sort of like generative modeling comes later in your studying path. You sort of study the first basic problem first, and then you move on to generative modeling, because it's generally harder in the computer vision field to think about generation. But in language field, not that it's easier, but somehow it comes more natural to people's mind that if you're studying this, you naturally think about, how do I produce language with machine? So that's like maybe one little difference. Also, at the same time, you want to solve all the tasks in NLP, and there are like thousands of tasks in NLP, like translation, like question answering, like making conversational bots, all those application areas and problems in NLP. So now that you've probably heard a bit of computer vision from the previous lecture, you might wonder, how is it different working in NLP versus working in computer vision? Say as a researcher? Well, a lot of them is the same. If you're using machine learning, you gather some data, you train some big model, it does things, you observe a loss curve going down. That's sort of like your daily activity. So of that is the same. There are slightly more work to process text data, just because in vision, we're lucky that images come in RGB or some other color map format, and they're already exist in a number, right? That you can easily do matmul, which is the most popular operation you have in deep learning. So they're already in a format that you can do matrix multiplication. They're already in a format that you can just feed into neural networks. It's slightly different with text. They come in in a string of characters, and basically you have to make sense of it, how to make computer able to read the text. So there's slightly more work to process text data and learn ways to process such data. You probably would try to get more familiar with probabilistic notions, because I think the starting of NLP, people already are thinking about questions of like, what's the probability of a sentence? What's the probability of words? So the notion of statistical modeling and probabilistics sort of exist early in people's minds, where of course that's sometimes the case in computer vision as well, but not as much, I would say. Partly because when working with language, we are dealing with tokens in a discrete world, and just very easy to think about, okay, for all the words in the world that exists, if you add them up, the probability should be 1, and then each word should have a little probability associated with it. So the notion of probabilistic modeling and statistics sort of like exists in your mind more often than if you're working on computer vision. And as I said, because they are discrete symbols, and because they are sort of harder to process, to feed into neural networks, you probably learn a few additional things to make text work in a neural network friendly space. So what I mean by that is, what neural network likes is that everything comes in as a float number, so that they can do matrix matrix multiplication. But text doesn't come naturally in that format, so sort of have to do a few things to do that. So neural network like that because it's fully differentiable, it's easy, there's no sampling. But in text, you encounter the break of differentiability very often, so you have to come up with sort of workarounds to do it. So that's like a few differences, but as I said, most of them is the same. So as I said, because text doesn't lie in that space yet, instead of continuous, it's very discrete. So first question we would find us facing is that, how do we process text? So at the bottom, it is a string of characters. So what's the first thing we want to do is we learn to use a tokenizer. There are many tokenizers existing these days. You can pick anyone you want to use. So basically what the tokenizer does is that it takes a string and it breaks it down to tokens. Tokens can be words. In this case, say the string is a sentence that says, my dog's my best friend. And you will break down to each word. And actually, I forgot to add here, but the period would be a separate token. So that will be a tokenizer. Another possible tokenizer will be character level. So maybe M is a token, Y is a token, the space is a token. So it depends on how you want you want your model to understand this string of data. You will pick a tokenizer that fits this data and fits your goal. There are many tokenizers you can choose. There can be character level, which means you just have maybe 26 plus some period and comma and space, and a little bit more, maybe 50 vocabulary size. And there's UTF-8, Unicode, and the most prominent one right now people are using more very often is what's called byte pair encoding. Basically, it starts from character level and try to merge characters together to become a token. So instead of having, say, M and Y, probably like my would be a token because it's used very often. So based on how frequently it is used in language, how frequently it is seen in language, probably FR would be one token because it's appeared very, very often in different words, and like TH, things like that. So byte pair encoding is kind of like a middle ground between character level and word level. Okay, so let's say we tokenized the string, and let's just assume for simplicity here that we're using words as tokens. So now we're given a string, now we have a bunch of words, right? That's the job done by a tokenizer. Now what do I do? Because machines still cannot understand words even as a token. So how do we represent words so that machine can understand it? Well, a very direct sort of thought is that you can represent words as discrete symbols. And in deep learning, you probably have seen from the previous lectures that we love one-hot vectors. We love representing discrete things in one-hot vectors. So for example, this is an example that people often use, motel and hotel. there are two words. They can be represented as one hot representation where only one of the dimension is marked 1 and all the others are being 0. So which dimension, it doesn't matter. It depends on how you sort the whole vocabulary. But say motel will be represented this way and hotel will be represented this way. Okay, so I have a question here and feel free to type in the chat. So what do you think the dimension of this one hot vector is? 26, okay. Yeah, that could be possible. 1D, right, it is definitely 1D, but I'm asking the length of this dimension. Yes, size of vocabulary, that's right. So thank you, Nathaniel. The answer is that the size of this one hot vector will be the number of words in your vocabulary. So for example, you can have 1 million. If you use character level representation, yeah, it could be 26. That's how many letters you have. But let's say we're using word level. So this is a word, and each word will be 1 token. Then so the size of this whole vector will be really large. Depends on your vocabulary size, but probably like 500,000 or a million. So that's kind of a problem, right? You don't want a representation to be so large, and it seems wasteful that so many of them are 0. Of course, if you're doing neural network operation, when you're doing matrix multiplication, the zeros will go away, but it just like takes a lot of space to even store them. So it seems wasteful. So a direct improvement from that, and also one thing that is being challenged here is that in such a representation, every 2 words are always orthogonal because they only occupy sort of 1 dimension in this high dimensional space. So that means like motel, hotel would be entirely orthogonal, which shouldn't be the case because you sort of want them to be close because they mean similar things. You're supposed to have motel and hotel closer than say motel and dog. So a direct next thought would be maybe we represent them with word vectors. So before I tell you like how to build word vectors and what are the methods of learning word vectors, maybe we can just stop and think like, if you are given word vectors, what do you want it to be like? What properties do you want the word vector to have? Well, first probably you want it to be dense, just as opposed to one hot vector, because otherwise you can just use one hot vector. You probably want to see, some kind of like a shorter dimension, a shorter vector, and a bunch of like float numbers, because again, neural networks love continuous numbers because they can do multiplication. So just like, this is totally imaginary, but if I were to build a word vector, probably I would want to see something like this. So you want it to be dense, and you probably want it to be meaningful, because why else are we building word vectors as opposed to discrete symbols? Meaningful in the sense that because they're vectors, now they exist in some high dimensional space, and all the words exist in the same high dimensional space. So if you somehow project that space into a lower dimensional, say in this case, 2-dimensional space, and you can visualize them, because we have difficulty visualize more than 3-dimensional. So let's say this word is represented by this is like 9 dimensions, but we project it into 2 dimensions, and we project every word into the same 2-dimensional space, and we visualize them. Probably you would want is that all the similar words or tokens, in this case is words, like all those about months, about numbers, years, all the things that have similar meanings, are grouped together. So that would suggest that this is a meaningful space that you've constructed. You probably want that. And another interpretation of meaningful is that you've probably seen this in news before, that proof that the word vector is really working is that you can do math with it. So basically you can have king minus man. That would equal to queen minus woman, or plus. So they have this vector relationship in the high dimensional space. The same thing. So from walking to walked should be the same relationship you got from swimming to swam. So if you minus walking from walked or minus swimming from swam, they should match. They should be very similar. So when I say minus or plus is in the linear algebra space. course. So with high dimensional vectors, you can do that. So the math should make sense. And yeah, the projection should make sense. So that's the thing that you sort of want a word vector to have. So with that goal in mind, we can start learning how to make such word vector possible. So one of the very prominent method out there, you probably have heard of, because the name is very catchy, it's called word2vec. It was invented somewhere 2013. And it is a framework for learning such word vectors. There are many other frameworks out there, but this one was quite successful. And it was quite easy. So there are two ways proposed in word2vec to learn such a vector. So let's take a look at what they are. So you can see that these two pictures are basically just a flipped version of one another. So the first one is called continuous back and forth. Basically, you're trying to predict a center word by using the word in a small window of the center word, the neighboring words in a small window of the center word. So why are we predicting words all of a sudden? So I thought we're trying to build word vectors. Well, the things, if you want to learn anything, in this case, you want to learn a representation of words, you have to give it a task to learn. That's how machine learning works. They need a task, they need an objective function, they need a loss function so that they can use gradients to learn things. So basically you're trying to come up with a smart task that by learning the task, they would automatically learn a representation that makes sense. And the representation in our case is we want a vector representation that has all the properties that we discussed earlier. So the task that word2vec came up with is one of these tasks, whether you are predicting the center word from the neighboring word, or you do the other way around, you predict all the neighboring word from the center word. So one is called continuous back of words, the other is called skipgrams. So it doesn't matter, they work, I think, approximately similar. Just for simplicity, we're gonna use skipgram, that is, you're predicting all the neighboring words with the center words to illustrate how word2vec is trained. Okay, let's say we're doing this. For each center word, we're trying to predict all the neighboring words. So remember how I said that you have to sort of like think things in probabilistic terms. So this is like the first probabilistic equations we're gonna come up with. I had a teacher in my grad school and who taught me that whenever you're teaching, whenever you're showing equations on a slide, make sure you make them really big so that people can see it clearly, and make sure you annotate them really well, tell them what each letter means, and make sure to tell people that don't be afraid of the equation. It's just an equation. If you fear them, they can probably smell your fear. So don't be afraid of them, be brave, and they will in turn to feel for you. Just some funny anecdote. So this equation seems a little bit intimidating, but it's okay, we can break it down. So now we're thinking of everything in probabilistic terms. So I have this picture right here. You guys see when the mouse moves?
Yes.
Okay, cool. So we have the picture right here. This is the skipgram. That's what we're trying to do. We have a central word trying to predict the neighboring words. So what that means in the probabilistic term is that I want to have a probability given central word predicting neighboring words, right? So this is like exactly this with the theta, because there has to be a parameter that you want to learn, because we're trying to build a loss function, objective function here. So that's what I want to do, because there are more than one neighboring word. So in this case, the window size is 5. And you're not predicting yourself, so you're predicting 4 of your neighbors. So you just do a product of all the 4 probabilities. That's what you can do with probabilities. And you do the product within this window. M in this case is 5, but you're omitting the 0, you're omitting yourself. So that's what it is. And you're learning not just for this single word, but you're learning for all the words in your database. So again, another product of all the possible T's. So T is going through the whole passage. Yeah, so that will give you a likelihood. So when you multiply a lot of probabilities together, each little probability is also called a likelihood. So we multiply them together, it comes to a likelihood of the whole sentence. So that's likelihood. We like likelihood. And normally in maximum likelihood construction, or in making a model that's trained with maximum likelihood, the objective function, which is what we train with, we train any parameters with, is usually just the negative log likelihood, what's called NLL. So this is even simpler. So of course, again, it's intimidating, but it's a very simple conversion from this one. So what you simply did is that you take a log, because we love logs in machine learning as well, because it has nice properties and it works well with positive data as this probability is. So probability is always between 0 and 1. You take a log, you make it negative, if you remember the shape of a loss curve, but it's monotonic. So if you have a big value here, a big value here. So the same, just take a log, and the amazing thing about log is that you convert all the product into a sum. So we like sums because when you're doing gradient descent, so with all the summing terms you can calculate gradients separately. So this is a very simple conversion. You add a log, boom, you have a log here. You converted all the product to a sum. And you simply like put an averaging term here because you want your loss to be within a bound. It's just easier to manage so that a longer sequence and a shorter sequence wouldn't be out of scale in terms of the loss they produce. So this will be the loss that you would want to optimize. You put a negative because you want to minimize the loss. Well, it's the same, but in machine learning, you sort of are used to minimize objective function as opposed to maximize, but it's just a choice that people made early on. Doesn't change anything. You can easily maximize an objective. But let's say we are minimize this negative log likelihood. So we're trying to train with this objective in mind. It's a loss, so you're trying to minimize it. If you're imagining how you train it, you would hope to see like a curve going down. So that's your loss. Cool. So seems like I've got everything except for, wait, what is this P, right? We're just like saying that we want to model the probability of center word, given center word of the neighboring word, but what is the P? Should I build a model with it? So that's the one remaining missing puzzle in this equation. What is the P, the probability? Well, here is like the innovative part that people inventing Word2Vec came up with. So they designed two vectors for each word. So there's a vector V if it's a center word, and there's a vector U if it is a context word. So when you are a word in a passage, sometimes you're center because you serve as, when the T is at your place, you serve as the center word. You are the sort of predictor. And sometimes you are a neighboring word of another center word. So that decides on, so that would decide which one of these vectors you would use. So each word has two vectors. And the smart math that people inventing Word2Vec has came up with, saying that the probability of a center word to predict a neighboring word, or sorry, the probability given a context word to predict a center word, context word. Oh, the probability of giving, sorry, so C means center because I mistake it as being context. They both start with C. So probability of center word, given center word predicting the neighboring word or context word, which we use O for some reason. So this is the same as this that we're trying to model here. Is gonna be the exponential of dot product, exponential block product. So this whole thing. It doesn't matter, right? This is something they designed and it worked. If you look closely, it makes a lot of sense. First, you have a dot products. So this is a very popular thing that people do in, at least recently in language modeling and in machine learning. People love dot product. It's a nice property that just tells you, if you have two vectors, it just tells you how similar they are. The larger the value of the dot product, the larger the probability that they are similar. So it's a very nice measure of similarity. So that's why people love dot products. So you're doing a dot product of these two vectors. Only remember that if you are the center word, you'll try to use V. So because that's designed to represent center word. And if you're not a center word, you will try to use U. That's the only difference. So that's your similarity, but you sort of want the similarity to be bounded. Like if I have a high similarity, if I have a high dot product, does that mean that I'm very similar to you? Or is that not high compared to everyone else's similarity? So always when you're designing a measure, you want to normalize it. So this is a normalizing term, basically everyone else's similarity, right? And I sum them up, I I normalize with, I normalize it. I use it to normalize my similarity. So this is a normalizing term. Again, a very common thing you see in machine learning. They're also like, you're always trying to normalize things well, so they are within scale. And exponentiation is also something very popular, popularly seen in machine learning. We like exponentiating things because it makes everything positive. Right, so that's like the three simple and very popular things put together in an equation and works really well. Okay, so now we have vectors. We are putting them in equation. We plug this into the objective function. Now we can start doing gradient descent. I'm not going to go into the details of doing gradient descent, but you sort of get the idea that, okay, now the theta is just all these. Oh. I wanted to ask questions. So what do we train here? What are the parameters? But I actually already told you the answer. That is the theta that we were supposed to train, that this objective function is dependent on, are all these UW and VWs. So if you want to calculate the number of parameters in this model, because this word2vec is a model that you train, it's going to be, if you represent each vector as small d, your whole vocabulary is big V, then it's going to be d times V, but you also time 2 because you have U and W. And just a practical tip, in the end, when you use it, you just simply average U and W. So you separate them because it's easier to train in practice, but when you use it later on after training, for each word, you probably just want one representation as opposed to 2. So you simply average U and W after the training. Cool, so that's how you train word2vec. Do you have any questions? I'm gonna stop here for questions.
Hey, Roseanne. There are some questions in the chat.
Okay.
I can read them.
I can see the chat.
Okay.
So, okay.
So one student is asking about what theta represented in the equations. I think it's just the parameters of the model.
Yeah, I was not able to see the question. Can you say that again?
What is the theta representing in the equations?
Yeah, so that would be right. That's the question that I was about to ask. So great, you're probably posting that question ahead of me. So after all this, I was going to ask, what do we train here? What's the theta? So the theta will be just the U, all the U and Ws. It's a lot of sort of unintuitive because usually you think of theta as the parameters that are, a small number of parameters. But remember, everything in deep learning is big, so you can have the whole vector, everything in the equation is the theta, right? There's no other things. So basically this is a good model that all you train are parameters and there's no data or anything. So that's why you train. Cool.
So we have a couple of questions in the Q&A.
Mm-hmm.
So one is, could you go over UW and VW in UW or VW?
Yeah, so basically we basically like made the true vector for each word. Let's say you have a whole data that has lots of words, my dog's my best friend. You just give my a U vector and V vector. You give dog a U vector, a V vector. Initially, you can initialize them to be all zeros or just random or one hot, however you like. Probably not one hot because you want a dense representation. You want the small d to not be the size of V. But like you initialize them, just say that, okay, now this is your vector. You are the word dog, right? So now you have two vectors. You're in charge of these two vectors. And I'm gonna train these two vectors as I go through the whole text. Every time I see dog, or every time I see dog as a central word or as a neighboring word to someone else, I'm gonna update your vector. So in the end of training, after you go through the whole text, maybe a few times, you're gonna have these two parameters of that word updated. And the end, what we obtain out of this method is that each word now in your vocabulary has two vectors. The vector can be, of the size 300 or something. That's what people like to use. But that's what UW and VW here is.
We have a good question in the chat. How does this method deal with homonyms?
It's in Q&A.
Yeah, sorry. Yeah, it's in if you click on Q&A in the bottom bar, it'll pop up more questions.
How does this method deal with what? Like the math?
Homonyms. So if something is spelled the same way but has different meanings.
Yeah, it does not. It does not have a way to deal with that. So that's the thing. This limitation of word2vec, it does not also disambiguate word senses. Like if you have the same word but it means differently, it's going to have the same vector built because of how it is spelled that way. Yeah, that's a good question, and that's the challenge that word2vec would not solve. And of course, later, spoiler alert, it's going to be solved by BERT or context-aware representations. But word2vec is going to be purely based on how it is spelled or how it is tokenized. If you make bank a token, and even though bank have many meanings, it can be the place that you withdraw money from. It can be a river bank. But because it's spelled like that and it's made one token, it's going to have one representation. So yeah, it's probably the average of both of its meanings or more than one meanings. But that's a good question.
We have one more question in the Q&A and then a raised hand. Do you have a preference? Okay, two more. Depends on when you want to get back to the lecture.
Oh yeah, sure. So I can see the question saying, since we are using the surrounding words to create some weighted flow representation of came across different sized sentences, wouldn't each word have a limit to how many surrounding words we could use to determine its meaning? Different size sentences. Yeah, so that's a design choice that you make up front. So you maybe want to say, I want my window size. So that's like a window size decision hyperparameter. Maybe I want my window size to be 5 because it makes sense because all this within the whole context, the whole text database data that I have seems like any sentence is at least 5 long. But of course you would come up with, you encounter a sentence that has only 2 words, then it would be a problem. But there's a simple workaround that you just mask the remaining 3 as 0 and it doesn't affect the learning because if they're all 0, everything is 0, the gradient 0. So them being 0 wouldn't affect the training. So there are like easy tricks you can do after you make a decision of how big your window is. But the decision of how big of a window you want to use should be like sort of informed by what kind of data you have. So if all your data is like 2-word sentences, you probably don't want to use a 5 as a window size. But yeah, that's a great question. Whoever's raised hand, feel free to speak.
Hi, can you hear me all right?
Yes.
I just had a question for natural language processing as.
Sorry, apologies. I accidentally turned off your ability to speak.
Okay, can you hear me now?
Yeah, you also have a background music, which is amazing.
Okay, sorry about that. I'll make it quick so the music doesn't deter.
Okay.
But I had a question for NLP as a whole. Do you know of any people who are trying to kind of widen the scope of it in terms of having it work for other languages, or is it kind of strictly right now an English forward endeavor?
Yeah.
Because I can see how bias will come in with this in the future, but then since English is such a big language, which doesn't mean that, it shouldn't be tried to, implement other languages with it. But what are your thoughts on that? Do you think that right now is the bias something that's, detrimental, or does it really matter? I don't know if the grand scheme is the correct terminology for it, but for what's trying to be accomplished, maybe at least for you or just for the collective, if you will.
Yeah, that's an awesome question. Thank you so much. I can't see your name, so sorry I didn't see your name. Oh, okay, thank you so much. Yeah, it's an awesome question. This is a question really just for any field, right? Any field, you sort of start with something, and everyone, if one person started that field with that thing, everyone's gonna come in and trying to naturally work on that thing. So yeah, English in NLP is very prominent. Almost, I don't know, I don't have the exact number, but I would say like 85% of energy of researchers are put in trying to understand English. that can be changed by just having more researchers out there speaking different languages. So that's why, again, diversity of the field is important. Again, why I am building up my whole career around trying to increase diversity of the field. Yeah, it's the same bias we see also in face recognition. You know, more data came from white male, so the system learned to just recognize white male much better than colored persons. In English is the same. Yeah, language model is more successful in English probably than in any other language, other than probably Chinese, because you also have a lot of researchers speaking Chinese and trying to build Chinese language models. And in the end, it's like who has the most researchers, who has the most resources, will try to develop models in that little domain. So yeah, this is definitely a problem to be aware of. There are many great efforts that I've come across trying to, you know, direct people's energy and people's attention to less spoken languages like African languages. There are great initiatives doing that. Definitely check it out there. Sebastian Ruder, someone that my friend is like sort of aware of a lot of those initiatives, and he's of course a very well-known figure in NLP. So those people are being very supportive of those initiatives. But yeah, this is an existing problem. We've definitely seen it. There are different initiatives trying to solve it, but we're definitely not there that we're being fair to all the other spoken or written languages out there. Thank you for the questions.
Thank you.
Okay, so I saw another question. Maybe I'll try to get to this one before we move on. How does a model able to classify, interpret, and differentiate between context word and center word? That's a great question. So the whole thing is that throughout the training, let me go back to this. Throughout training, every word gets to be a center word and neighbor word, because you're basically just scanning over the whole corpus of your text. So that's how the whole training works. So here I'm only showing a snippet, right? This could be my dog is my best friend. So is becomes a center word, but as you're scanning, so the window like moves across the whole text, the word dog would get to be someone else's neighbor and get to be the center, and get to be the neighbor of many different words. They all have chance to do that. So that's why both of the vectors, center word vector and context word vector, are being trained. That's an excellent question. Cool, I think I'm gonna move on. So let's say we train that, right? Seems like we've got a, we've got an objective function. Gradient should just work nicely, because across the whole equation, there's nowhere we break continuity, nowhere we break differentiability. So gradient should work nicely. Gradient descent will help you train this vector. And it is very successful. It is a very successful method. In the end, after training, there's a site that you can basically play with a pre-trained word-to-vec with a lot of words. And you can see that they nicely cluster together from different notions. And you can easily query a word and find the most similar word to that query word, and it makes perfect sense. So that's like sort of ways to validate that you've obtained a good representation of the words. They cluster together while the similarity sort of matches. There are different like ways to explore this word-to-vec explorer, different ways to explore different spaces in the whole high dimensional space. I think I saw a question early on in the chat asking how to project into a lower dimensional space. There are many ways. You can do PCA. The very popular way these days is called t-SNE. But basically it's just some simple math to project the higher dimension to a lower dimension and try to pick the low dimension to be the most determining one. But here, yeah, whenever you're viewing something in two-dimensional, remember that it was existing in a higher dimension. It is projected here. So based on the method of projection, sometimes it would not make that much sense. So sometimes you will try to run it a few more times if you're doing t-SNE until you probably find a very successful or very sensible direction. So yeah, in this visualization, you can see that things also make sense. They're close together. If your one word is it's just a plural of the other, and it seems like the direction also sort of matches. Not sure if exactly they're close, right? From this one, so it seems the other way though. Yeah. Well, the whole model is trying to learn many things. So we just spotted maybe a little bit imperfection here. So from banana to bananas is this upward direction, but then from pineapple to pineapple is going the opposite direction. Kind of interesting. Cool. With that, I will sort of like, that's it with the word2vec section or learning word vectors section. So are we there? And we just spend enormous effort trying to learn word vectors. Now with each word, we can have a dense representation of it. So are we there? So far we figured out how to represent the very basic unit in NLP, that's words. And after the whole learning, we probably got ourselves a huge matrix that is of 1 million, say that's your vocabulary size, times 300, say that's your dense representation size. You got yourself a huge matrix. Basically, it's a whole big lookup table. Now with any word, you can find a 300 sized vector to represent it. But is that it? There's some problem with it. It is a static representation, meaning that it is trained, it is fixed, it is there. It doesn't adapt itself. So as the few questions that you guys raised, if it's a homonym, if it's a word that has many senses or many meanings, it won't be able to differentiate that. Also, it doesn't adapt. If like 100 years later, this word now means slightly different from before, this representation will be outdated and you have to retrain it. So it doesn't adapt with the context, with how it's being used with even time. So kind of problematic. And at the end, we are right now just figuring out how to represent word, but what about the rest of the language? Language is much more than just a collection of words. There's a structure, there's how you say things. Even for the same set of words, if you rearrange it differently, probably, you would be saying very different things. So what about all the rest of it? How should we model that? Because to be able to produce or understanding or do anything with language, you should be thinking about modeling all the rest on top of the words. So what I'll say here is that word vectors is a very good start, basically by converting words into a dense representation or numeric representation. It now allows any practitioners to start building models. So with computer vision, it's easy. So the data come to us with RGB values. We can already start building models on top of it. So now we've spent all the time just to convert each word into basically like an RGB-like representation, but now you can start building any models with it. Like you've probably learned convolutional neural networks, you can try doing that. You can try all kinds of model architectures. So here is where the fun starts, because now we have representation, you can really just stack layers on top of them and try to design loss functions for your specific task. But what models and what tasks? So later of the lecture, this part of the lecture we'll go over like a few possible models that you can build with this representation and some tasks you can think about doing if you're trying to work in NLP. So one stark sort of difference of NLP versus the other field is that it has a lot of tasks. So if you think about your learning language, there are just so many things you can do with language. You can try to model a language, that is, you're trying to have a generator that speaks, that generates language as a human would. And there's translation. You can work with more than one language and try to find one-to-one mappings of each other. There's question answering. There's conversational AI that's building a bot that speaks to you. There are many things. There's sentiment analysis. You have a passage, trying to decide whether it's a positive passage or negative passage. Say if it's a movie review, you can try to have a machine read that and tell you whether this person thinks highly of the movie or bad of the movie. There are many things you can do with language. Actually, because there are so many things, and there are sort of like benchmarks people put together. It's called Glue, and later on there's a more advanced version called Super Glue. The website is here. Basically, it has all these tasks in this benchmark site, and anyone proposing a model would try to use the model to test it on all these tasks and report scores or metrics on all these tasks. So just in some way, like it's sort of like harder to propose a model in NLP because like you have to really be good at all these tasks. Even if you're just trying to get ahead with Glue, there's this many tasks. Not to mention if you're trying to get ahead with Glue and Super Glue, as opposed to maybe if you're working in computer vision, you can just have a model that's great at image classification, have a model that's great at producing top-line accuracy on ImageNet, and you're done. That's a paper. but sort of like the trend that we're seeing is that any NLP model, they have to be validated with a lot more tasks than vision tasks. But the good news there, I think that most of tasks are similar, at least of all the recent models that we've seen proposed. They pretty much, perform similarly well or unwell across all the tasks, although they're very different. Some are about reading comprehension, and some are about answering some questions, multi choices of questions, for example. But yeah, but that would be like what you would want to do if you're working in an NLP, trying to get to know all these tasks and try to have your model sort of like perform well in each of them. Speaking of superglue, which is the more recent, more advanced task collection, for both of the sites, there are leaderboards, and the same for superglue. There's a leaderboard, basically just like ranks. You can submit your model to the site and it will calculate all the scores based on all the various tasks combined together, showing you how well your model is performing. We will stop here for a second and tell me like what you see in this picture, what you see that is surprising or unsurprising, just what you see here. I'll be observing the chat. You can type in the chat if you want. And by the way, this just happened, I believe, a few days ago. It was not like this a few days ago. A lot of Roberta, yep, that's true. But the really thing here is that human baseline is here. So when they started this leaderboard, they established a human baseline. They probably, I don't know, but like asked a few humans to perform the task themselves and make their scores here. And for the longest time, no AI models were able to beat human baseline. I think, I could be wrong, but I think this just happened a few days ago that number 1 and 2 are now models instead of human baseline. Kind of a very important moment in human history, I guess, or at least in this small domain of tasks that we have machine there outperforming human in terms of all these tasks, understanding language and doing all the things with it. I don't know, it can be surprising or not surprising after you've seen so many news about machines beating human at, chess and Dota, and probably it's not super surprising that they're beating us at language. But at the same time, sort of like language is a thing that we have, right? It's not math, it's not, you can't do it with calculation. So I don't know, depends on where you stand. You probably have different emotional reacts to it. But yeah, that's the thing that I was trying to allude to. Cool. So we have all these tasks, like hundreds of them, thousands of them. I want to focus on part of this lecture on one task that's sort of like, you've probably see it a lot. It's called language modeling, and it's making a lot of progress. And also it's a task that's really simple. You're just trying to produce language. It's like in GANs, you're trying to paint a picture. And that says a lot about a model. If a model can produce language, that's just, represents sort of a base understanding maybe of that model of language. And all the GPT-2, GPT-3 models that we've seen out there belong to this task. They're trained basically to do language modeling with a very simple objective. That is to predict the next word. So language modeling is the task of predicting what word comes next. If you want to write in math, again, don't be intimidated by the math. It's just, symbols, same as the natural language. So this is the same thing again, but in math. Say if you have a sequence from x1 to xt, that's how long your sequence is. Those are the words or tokens. Basically, you want to predict what the next word is, meaning you want to have a probability representation. Again, probability really comes heavily in NLP. Of the next word, given all the previous words. So that's what you're trying to do in language modeling if you're trying to speak in math. Yeah, that means a text generator. If you are training it well, you should have a text generator. You have a model that knows what's the most probable words after, then you can generate that word, and then you put that word back into these conditional term, then you can generate the next word. So you can keep going, and that's how all the advanced language models these days are working. Cool. So it is a text generator, but also at the same time, it is also a model that assigns probability to a piece of task. Why do I say that? Basically what I mean is it is a model that can give you this probability, conditional probability, but it's also a model that can give you a joint probability. So this just basically saying that what's the probability of this sentence? Say, my dog is my best friend. Is this a probability of like 95% or 20%, whatever that means, right? Of course, people have debates over like, what does it mean if you say how likely or how probable is a sentence? But let's say we have a definition on that. And this is a model that's able to tell you that. This is how probable, how likely this sentence is to be seen, like maybe in the wild world, or how often or how likely you're gonna hear this sentence, basically like that. So this will be a model that's able to give you that. Because you can do it with the simple math, because if you are following this Markov assumption that each word's probability is only given by its previous words, then this joint probability is basically just a multiplication of all the word probability from word 1 to word 2 to word T. And of course, except for word 1, all the other words are conditioned on their previous words, but basically it's a multiplication of all of them. Or in a very more concise representation is a product of all of them. This is the same as this one. It's just written in a more concise form. And see, our model is able to give you that. So that's why our model is able to give you this joint probability. So that's basically explanation why it is a text generator, but also at the same time, a like probability assigner, whatever you want to call it, but like it evaluates how likely your sentence is. Also, this, just so you know, is also called an n-gram, or in this case, a t-gram, because the length is t. Before deep learning, almost all language models are generated or are built with an n-gram. So n-gram just basically says if I have n tokens in a sentence, I want to know the probability of that sentence. So that's your n-gram. And I should have probability of any phrase or combination that has n length. So it was a very sort of like brute force method for language modeling back in the days. You just have a huge table that documents everything you see in this corpus was the like 3 gram of everything, every possible 3-word combination. I want to count how many times they appeared over all the number of times any 3-word combination appeared. So you have a probability, and you use that simply as a word generator. That's one of the very earliest and very basic language model back in the days, just so you know. So yeah, so with that, we sort of know that language model basically existed from way before, right? Around maybe 1950s, we already have n-gram. It's it's like not really a machine learning model. You just count the frequency, the occurrence of all the n-grams, in this case, maybe 3 grams, based on this Markov assumption, and you build a huge database. And then when you generate, you sort of draw from that database, because you have probability, you can pick the most probable word next. So back then with n-gram, you're able to generate a sentence like this, which sort of like is already very impressive, given how easy this model is. So they were able to generate samples like they also point to $99.6 billion for 204.063% of the rates of interest stories as Mexico and Brazil on market conditions. Sort of like doesn't make much sense, but it's sort of fluent, and it could be something that you see in the internet. That's the point. So it's pretty impressive with such a simple model, but that's the 1950s. Moving forward to 2011, which is like sort of like people are starting to work on RNNs and language models again because of the like renewed interest in machine learning and in neural networks. And RNN back in 2011 was able to do this. So if you give it a prefix or sort of like a condition, you write this, the meaning of life is, and then you ask the machine, please complete the sentence for me. And it will say that meaning of life is the tradition of the ancient human reproduction, just less favorable to the good boy for when to remove her. Somehow it doesn't, starts to lose sense as you go on. That's also usually a thing you see in language modeling, that in the beginning, the sampling is pretty well because this condition is well put, right? Human read this condition. So this word would make the most sense. But the second word will be conditioned on, will be conditioned on the human input and the last generation. So as you go on and on, you're just like basically feeding your own produced language back to your condition sort of just like diverges really fast. So that's back then. In 2016, people start building larger RNNs and a better variant of RNN called LSTMs, and you're able to generate basically better language with it. Moving forward, like a few years later, people invented transformer, which we're going to be looking at later on. And this is a character level transformer that people build, and is becoming definitely more impressive than previous results. And remember, this is a character-based model. So the model generates each letter one after another. So the fact that it's able to spell really well for almost every word, there's no, misspelling that you can see, is really impressive. But that's a transformer, so it's a better model. You can build bigger transformers. I'm sure this is what's called Transformer XL. So with bigger transformers, you can have better samples. Basically, that's the thing that we already know. We want to make a model bigger and bigger. We want to use more and more data. And this is the GPT-2 age that in 2019, we're able to, or people out there are able to train a language model that's called GPT-2 that's giving you really basically amazing stories. So you give it a prefix. Basically, it's just a made up story, right? In the prefix, you want the model to finish the story, starting with that scientists discovered unicorn, and they spoke perfect English, and they discovered a unicorn in the Andes Mountains. So the model is able to sort of like finish telling the story, even though it started from really a nonsensical start, but telling it in a very believable way, and very, very interestingly, is able to make connections to what's said in the prefix. For example, the prefix mentioned scientist, so you're trying to put doctor in the sentence, evolutionary biologist, sort of like drawing from scientists, and in the prefix there's Andes Mountains. Is able to make reference to that by saying University of La Paz, which I believe is a city next to Andes Mountains. So sort of like this is amazingly believable and amazingly able to accumulate all the knowledge basically out there in the wild that some humans may not be able to possess. So that's like the moment of GPT-2 that people are really amazed by the capability of language models. So we've just gone through a few samples. We were looking at samples to judge like how well language modeling have been through over the years, from early 1950s to basically now-ish. And of course, I haven't shown GPT-3 results, but I'm sure some of you have played with, and it's just again very, very impressive, and basically it can definitely pass the Turing test and pass you as a human speaking. So we've seen that. We are going to spend a little bit of time to see what the model is like. So we've seen text samples from transformers, and I told you that this is an RNN, this is LSTM, but what are they, right? So we're going to look at it like very, very briefly what they are in terms of models. Let me check with time. So I think we're pretty good with time.
Yeah, Roseanne, we're supposed to finish at 11:30, but we can go over a little bit, like 15 minutes.
Oh, cool. Also, I'm happy to, go faster or slower. So there's a question in the chat asking the task is completely made up by the model. Yes, that is true. So it is a model, it is a language generator. Anything you see here is made up by the model, except for the underlined one is typed in by human. So human is basically asking the model to, complete the story after this period. Read all these and then start writing yourself until you're until you're comfortable to stop. So yeah, that's how impressive this model is. Basically all written by AI, by a model, a big transformer. Do we have any other questions? Cool.
There's a raised hand.
Hi, can you hear me?
Yeah.
Yes.
Yeah, it's a question I had on the chat. Also, I wanted to know, like, you said that you predict words based on like the words that are around it or come before it. So I wondered, what about like if it's the first word or the start of the sentence? So, and then you have no previous data or words to predict from. So how basically do the model learns from that?
Yeah, so again, so any model sort of have a context length that you set up front. So you're telling the model that you're able to look back, 100 words or something like that. But with transformers, you're able to, so with RNNs, that length is unlimited, because you just see, we're gonna see how the model works to know that RNNs, they just process word one after another. Basically, it sees every word that has ever gone through in this generation of this passage. But with transformer, it also sees almost everything up to a limit that you set, and is able to pay different attentions to different words. But basically, yes, the generation here probably like already sees everything, even more before it, if you were to type more before it. I hope that answers the question.
Yeah, and a quick other one is you always been said like let's say like tones, expression, and like double meaning. It's pretty hard to translate to text. So I'm wondering like conversational AI, how does it like interpret those things, which is pretty hard in text? Like let's say you're sending a text, it's pretty hard to get the tone and all those other meaning that it's like not shown in conversations.
Yeah, it's hard. But at least like recent development has shown you that with enough data. So if you have enough variety in your data that has different tones, and if there are people, they're annotating the tones and like creating subtasks for the model to learn. So the language model basically just learns to produce the next word. But if at the same time, you're also telling the model have a separate head, what people call in the model, to basically classify the tone, or at least let it be aware of the tone. Trained with that method, sometimes the model will be more aware of the tone and respond in, according to the tone. But yeah, it's a very hard problem. It's an ongoing research. If you're interested in research, definitely, you can start doing it, because no one has really completely solved it yet. That's a great question.
Yeah, thank you.
Yeah. Cool. We've seen some samples, and you've heard words like RNN, LSTM, and transformer in those samples. So now let's just look at what they are. So before we go to RNN, so basically, why do we need RNN? So the first question probably comes to mind is like, can we just model with CNNs? Because we already learned CNN if you attended last lecture. That seems like it's able to process a sequence, right? So why don't we just try using CNN, because we want to know why we would need an RNN. So yeah, you can totally use a CNN. And how CNN process a language would be like this. So again, you put language comes in as tokens. So say for each word, you just lay them out like this. And because we already did the word to VAC things, so now each word is represented by a vector. So I use this like long box representing a vector. It's just like string of numbers. So now great, each word is represented like this. You remember how convolution works? A convolution is a window that scans over the whole space. Usually when you do image, you would have a 2D window by like 3x3 or 5x5. But because word exists in a 1D sort of dimension, if you're not accounting for this 300 in this dimension, so you would have a 1D CNN, that's what you would have. So in this illustration, I'm using a window size of 4. So you have 1 times 4, the window size, and you have the window go through the whole text. For each 4 words, you're gonna have a representation. Next to 4 words, you have a representation. So this is just a common, excuse me, common CNN that you would build. And in the end, you summarize everything into one representation, which say represents the sentiment of the sentence, something like that. It's harder to use CNN to do language modeling, but it's not impossible. Basically, what you do is you pick the next word that's after the last blue word that you see, and you use that as your objective. So it can be a language model in that sense. It's sort of harder, but yeah, for various reasons. But yeah, of course, you can use CNN already. You don't need to learn any fancy new model. You can already start processing text with a model that you're very familiar with. So yes, but of course there are limitations of it. That's why we want to come up with new models. So the limitation here is that it's a fixed length input. So one thing that you probably know with CNN is that everything comes in has to be the same size. With image, it's easy. You can basically just resize every image into the same size, say like 224 by 224, without losing much information. Of course, if you downsize an image, it's blurrier or some information is lost, but it's like sort of okay. And that's what people do when they build a model on top of ImageNet. The first thing they do is they convert each ImageNet image into the same size, say 224 by 224. But with language, you can't really do that. If you subsample languages, you're totally breaking the language apart, and it's not learning the right thing. So really, we need a neural network that can process any length input and be okay with it. So that's how recurrent basically came around. So recurrent is a structure that is able to take inputs recurrently, which is why it's called recurrent. You can consider it a regular neural network unrolled in time. I'll explain what that means. So you have the same series of words, right? But then every time only one word goes in, as a neural network would do, it converts that word into a hidden state. We call hidden state, but basically there's a layer in the neural network that converted to something else. Maybe I plot this longer because usually the hidden state is bigger than the original input. So you have a hidden state, you just do this. So this one line here is just a very normal feed-forward neural network. It can be an NLP, right? It can be convolution, whatever you want. But then what comes after it is that you put another word in, at the same time you put the last hidden state in. So now it's the same neural network. You are using it another time. So if you're trying to program it, you can imagine a for loop, right? You first process this word. Now you're processing the second word, but using the same parameters, same model. And you're feeding the hidden state you got from last time into it. So each time it takes two inputs, one from your word, the other from your previous state. So you might ask, like, what do I do here? Here seems like I just have one input, that's the word. Well, usually you would have a hidden state that is H0. I didn't plot it here, but yeah, you would have an input. It can be initialized as all zero or just random. It will learn to be more and more sensible. So you do this for every time step until you reach the end of the sentence they're going to process. So this is very nice because it doesn't matter how long your sentence is. And one important thing here is that the weights are tied, meaning like every time you use this model, you're using the exact same weights as before. Because if it's untied, if it's all different, then it again cannot adapt to any length. Only because it's the same model, you keep using it, you're basically like unrolling the same model over time. That's why we say unrolled in time. So that's how a recurrent neural network works. Any questions on how it works before I move on to pros and cons of it? Cool. Yeah, sort of easy. You just like look at one word per time. Seems like makes sense, right? When we hear a speech or we read a text, probably we also read one word after another. So the pros of this model is that it can process any length input, great, and however long your sequence, your input is, it comes up with in the end like one fixed length representation. So that's very useful. You can sort of like learn to read the whole sentence and come up with always like 1,000 lengths vector that represent all the knowledge you've learned with the whole sentence. So it's very easy to build downstream models with that. So you can try to map this representation with any MLP into, say, a topic modeling model or a sentiment classifier without having to think that, oh, if that input sentence was longer, do I have to make the classifier size differently? No, because any length of the input, you always come up with, 1,000. So you can start building your MLP with like 1,000 by 2,000, 2,000 by 3,000. You can design a model right away without caring about what's the output length. It is supposedly able to capture long-term memory because you basically read every word. The same model, read every word. There's no window length. It's not saying that any word outside of the window of 100 I would not be able to read, because the way that it works is that you read every word from beginning to end. There are disadvantages that is sort of slow because you can't really parallelize over time. So time 2 has to come after time 1. So the unrolling in time is a blessing, but at the same time a curse because now you cannot speed up better than process all the time at the same time. So that's slow. And although we say that long-term memory is sort of a given, but people have found out that it only works in theory. Like in theoretically, you should be able to remember things from very early on. But what we found is that as you go further and further in time, they start to sort of forget what's said in the beginning, which makes sense, right? If you're human, you keep reading. After, I don't know, 200 pages, you probably forgot what the first page is about, if you're asked a question about the first page. So makes sense. There's also practical problems, what's called vanishing gradients, because practically what this is a super deep, if you're unrolling in time, say for 100 steps, it's basically 100 step, it's 100 deep neural network. And we probably already know that there are vanishing gradients problem in deep neural networks. People were not able to make networks very deep due to that. And a lot of like workarounds had to be proposed, like ResNet was proposed, and all of like DenseNet was proposed to basically counter the vanishing gradient problem. But with recurrent network, this problem is basically just inherent, because how you unroll it, you are building really, really deep neural network, and where all the weights are tight, it's very hard to train, basically. So, which is why people came up with fancier architectures to try to solve all those problems. It never solved the problem of slow, because as long as it stays within the family of recurrent neural networks, it still have to process word one after another. But basically LSTM and GRUs are proposed to solve the task of forgetting context from early on. And LSTM was really a very popular invention. With that, I think basically by the time they was invented, basically just wiped away like all the benchmarks that used to be achieved by RNN. So it became the most favored child in the RNN family. So there are many blog posts analyzing what each gate means. I won't go deep into it. Basically, like you still have a 1X come in and 1H comes out. So this is O, this is an H. So you have 1X come in, 1H come out, and possibly one also output comes out. And basically, instead of just map it with just one layer, they create all these gates. So you can have a forget gate. So you can decide whether this is an input that I would want to forget, or this is an input that I want to save in memory. It adds memory to basically the layer. So it's like sort of rather complicated, but with this complicated design, you're able to overcome the vanishing gradient and the long-term memory problem. That's why, like, anytime you find a model that's sort of like underperforming, you as a researcher, you should think that, oh, there's a chance for me or for some other researcher in the field to propose better models. So never get disappointed just because your model is not working. See it always like a failure of your model has a chance to propose better models. So this will be a great example. So all those variants, those fancy RNNs, basically dominate the field until around 2018, until you guys probably know transformer came about. So how the way that I want to explain transformer, of course, I want to compare it with CNNs and RNNs. So a recap of how CNNs work. You probably remember like a moving window scanning the whole sequence versus taking in input one at a time. And transformers, or in this case, this is just a part of the transformer that's called self-attention, really is a new member of the family. So now you can go out and tell people that there are 3 types of model you can build. 3 families of model you can build. You can build a CNN, you can build an RNN, you can build a self-attention. And almost all the 3 models are applicable to almost all kinds of problems. You know, CNNs work well in computer vision, but you can also use RNN in computer vision. It just doesn't make that much sense, but it's able to take, you know, one pixel after another and in the end make decisions. You can also use CNN for sequence that we have seen. So self-attention is the same. You can use it basically for any application because it's the same. You process a bunch of inputs and come up with an output. And the whole thing is trainable because every operation is differentiable. So without going into super details, what self-attention is that you can see that it's more complicated a mechanism than all these. So these, basically, whenever I just put a direct arrow, it just means that it's a simple match-mill matrix multiplication. But here it's more complicated than matrix multiplication. And first thing you will notice is that it allows this like pairwise computation early on. So for all the other models, basically if you are an input, you just go ahead, do your own thing. You never interact with the rest of your peers, the other words basically. But then with self-attention from early on, you're asked, so the operation asks you to compare yourself with your peer, with other words. So this compare is a function that you can use anything and is a dot product actually. So that we've seen before. It's a very favored operation that machine learning researchers just love. So let's say you compare yourself with the word before you, you compare yourself with the word after you, you can compare as much as you want. Actually, what people do is they compare with everything. So it's a pairwise comparison you can do. And after the comparison or the similarity calculation, because it's a dot product, you come up with a number that you can say, okay, how similar I am to this word, how similar I am to this word. That's a measure that I sort of have in mind. And then I multiply their representation by the similarity. So this is a multiplication. So I'm sort of like taking part of their representation just because I'm similar or not similar to them, and then add it to my representation. So this whole process is very beautiful and makes a lot of sense that I'm building my representation not just based on my previous representation. That's all the previous models are based on, that my later representation is based on my previous representation. But here is my later representation is based on my previous representation and everyone else's previous representation. So it's a very beautiful design, makes a lot of sense. Totally changed the field with this simple change of the architecture. And amazing thing is that, so I already talked about, it allows early pairwise interaction. It is multiplicative, so that's also one thing that is able to change. That is like there's a multiplication here. So if you recall all the other models, there's no multiplication of activations. So you, of course, every process you multiply yourself to the weights, but this is the one architecture that allows a multiplication of activations. So so this is your input. After your comparison, this is an activation. You're basically multiplying two activations together and come up with something. So it allows the multiplication to exist in the model. That's probably like one of the reasons that is successful. It is permutation invariant because you're doing pairwise computation. You don't know this word is before you. You just know that it's a word out there that you want to compare to. It is both a feature and sort of a bug. So later on, people proposed positional encoding to overcome that. So because they want the model to still know like where it is in this sentence. So, but this is a feature of self-attention. It doesn't know where each word is. Basically, it sees all the words as a collection, like a bag of words. It is very parallelizable because the same thing you do with this word, you're doing with other word, we're doing with this word. It doesn't depend on like this word has to be processed before me or something. So it's totally parallelizable. That's amazing. Allows you to train a faster and faster models. And as we see later on, that basically all the great success stories out there with big models is just the ability to train with large data and train really fast. And also it makes intuitive sense if you think about it. Like, of course, when I read this word, I kind of want to know like whether it is referring to any other words, like the attention, the idea of attention that is paying to the other words makes intuitive sense to us. And you can easily visualize the attention because it is an actual attention. There's a number that you can come up here. So this, after the comparison, there's a number. So you can visualize it. And also the authors of the paper, that's called Attention is All You Need, provided a notebook that you can just play with attention. So for this sentence, the animal didn't cross the street because it was too tired. So this it is paying attention to every other word, and you can see that it is paying more attention to animal. So it knows that this it is an animal, and its state, like too tired, is also paid more attention. So it makes the model very interpretable, at least more interpretable than any previous models. That's also a very nice feature of self-attention. So self-attention is basically the very important building block of what we know later as transformer. So transformer is basically self-attention, but making it more complicated. Now you have multi-head attention kind of here. And they add a bunch of like normalization, residual connection, which is like here, and a feed-forward network and all those things. So when you're in the space of designing a model, this is like a Lego game. You're putting all the pieces together and try to see which one works. But So they tested this Lego piece and it worked really, really well. And it is proposed, of course, in this paper called Attention is All You Need, probably the most popular paper in the last, from then to now. Like no other paper has achieved a better citation than it, because it's such a revolutionary model type that changed the whole field of NLP. So with this model, it is able to sort of like open the whole era that's called large language models. So before the invention of transformer, people were playing with RNNs, CNNs, and actually people are already playing with self-attention, but just not in the whole transformer block. And those things all has its own drawbacks. So it prevented people from really building really large models, doing things really fast or able to process all the big data. But with transformer, basically people are able to build really, really large language models. And by large, this is what I mean. So this is basically a snapshot of all the models that we've seen from, say, February 2019, all the way to May 2020. Different companies are trying to propose different models. So you can see the release date as kind of close to each other because everyone wants to compete with each other in building larger and larger models. And though the table is telling you is that across the time proposed by different companies, you can see the model size getting bigger and bigger. So this is a number of parameters. This is like never been seen before, this level of parameters in vision or in any other tasks. Because in NLP, you have so many text data, which I put here. So that's the amount of data they use to train this model. They are all, the training times are all in months. And of course, depends on how many GPUs you use and how much budget you have, but it's just massive, massive training using massive data and are able to build a model size that's never seen before. 1.5 billion, that was, super surprising until later on. Of course, with GPT-3, you have 175 billion parameters, just a lot. And it's able to, of course, process more and more data. I got all those numbers from their paper. Some may be different. Like this one is smaller than this one, but I think some are reporting like compressed data size. Some are reporting decompressed data size. It's kind of not very consistent across the papers. So yeah, take this with a grain of salt. But basically you can go to each of their papers and realize, how their training scheme is probably like very similar. So there's honestly very little really creativity in terms of like how they design the model or what they use smartly with the data. Basically, the whole creativity part is that they just made the model bigger and bigger, that is able to devour more and more data. And of course, performs much, much better. They, of course, evaluate all those models against the leaderboard or the standard test that I mentioned before. And also all of them are language models, so they're able to generate language, so you can basically just see for yourself, look at the past and know how well this model is. If it can pass you as a human, if you can't tell whether it's generated by a machine or a human. So that's what we're living with these days, all these huge language models.
Roseanne, just in the interest of time, so we're a bit over now. Do you want to take maybe like 7 more minutes and try and finish around 11:40? Is that doable?
Yeah, I can do that.
Okay.
I have a part that I think I'll just omit, but the slides
also,
here, so yeah.
Real quick, we have a question from earlier from Sabrina.
Okay.
Nikita, do you want to unmute Sabrina and she can ask your question? Sabrina, if you're still here.
Sorry. Was I don't have a question. Sorry.
Okay. Yeah. if it comes up again, feel free to ask in chat and we'll answer it.
Yeah. Cool. Cool. So basically we are in this, like, this is where we live with now, huge language models. And it has made great things available, right? We're able to see, like, for ourselves what great AI technologies can do, how they can really mimic human behavior in terms of language generation. And at the same time, they make the field a little bit more exclusive because they're so expensive and require so much resources to train. Basically, they only, the places only able to do them are just the big companies with a lot of, fundings. So most make them really inaccessible to those outside of those big labs. Which is why I'm asked a lot, very often these days, whether it is still a good time to get into NLP. If all the big contributions are made by giant tech companies with unlimited resources. Because there's a vicious cycle here that if you want to, well, if it's great to get into NLP if you can just directly join those big companies and work on these large models. But as a student, you probably need some kind of a certificate to be able to do that. They probably want to know that you already work on NLP for a while and know all the terms. You can study on your own, but it's very, very hard as a student in academia setting to be able to get your hands on, this big model training. So that's why I'm asked a lot of these questions a lot. And of course, in the end, it's still up to all you guys, like what your interests are. Do you find this piece of work interesting to make your career choice? But I also want to give 2 reasons that I'm prone to answer yes. So one of the reasons that don't get disappointed by big models made out of big labs because they have a lot of resources, because there are still creativities to be uncovered with small compute. And the second point is that it's actually a very crucial time to get to NLP. I'll get to that point later. Basically, the part I will going to omit for this lecture because in the limit of time is that I wanted to tell you this one example of creating creative NLP work with small compute. Basically is it's a shameless plug. It's a paper of my own that's called Plug and Play Language Models. And all we do here is 1 GPU. We didn't use large compute. We didn't train anything, so we don't need to use large compute. But basically, I'm going to skip this. So let me just move on to the next section. But basically what it does is that you take a GPT-2, which is pre-trained, which is released out there, and we are able to steal its generation to whatever we want. So we can make the prediction, the generation of the language more negative or more positive. And this part that I'm going to skip for now basically tells you how well this method works, but also there's no big compute involved in creating this paper. Of course, when delivering the method, you need a GPU, but that's it. The whole time, anything presented in this work, which is accepted at ICLR 2020, can be done with 1 GPU. So don't get disappointed if all you see out there are big contributions made by thousands of GPUs trained for months. There's still work you can do, even if you're limited by resource. So let's move on to, hopefully with that one data sample that I happen to skip, I'm able to make the point that there's still creativities that are almost orthogonal to how much compute you have, because those computer people can make creativities in their direction, but your direction is mostly orthogonal to theirs. And actually a lot of creativity actually comes about when you have limitations. That's a thing that we see in science over and over again. So don't get disappointed if you are thinking about joining, you love this field, but you are intimidated by the big contributions made out there. The second point is that, also my last point, is that it's actually a very crucial time to get into NLP. So the time that I prepared for this lecture, which is yesterday, is sort of like a big day in history. We've seen this happening. And this is just one snapshot of one of the news articles. There are many out there that you probably already known, and for those in the US are also very gravely affected by this incident. And I want to point out this one just because this is a picture by someone that's a known QAnon conspiracy theorist, a picture of him. And we all sort of are aware of what we are dealing with these days. There's a big division in our country and also across the world. And to some extent, we know that that's prepared by the social media. If you have watched Social Dilemma or other documentaries. So these things are sort of what's behind the force to make it happen is the advance of tech, the advance of, so many things people can read out there that they can basically just read whatever they want to read. And because there are so many misinformations that to some extent is made possible by the advance of technology, including NLP. So of course, as someone working on technology, you also want to say that, well, I'm only in charge of making the theory, making the model. I'm not in charge of, creating all the harms out there that, that's not something I can foresee. But something I want, this like half true. Of course, we are computer scientists. We care about the essential algorithm, but something we want to probably say more to ourselves that is that to be more of a responsible human, that while you're creating the technology, maybe think more about the harm that it can create, or how it can change culture, how it can change people's mind of thinking. Because people's mind, as it turns out, are way more flexible than we think. They can really just believe in anything out there. Just a point that I wanted to make, just because this lecture happened in this crucial time. So what we've covered in this lecture is basically some of the basic elements of NLP, including word vectors, language modeling. We've covered RNNs and two transformers. I wanted to tell you that small compute research still matters. And I wanted to basically say that if you find this field interesting, don't be intimidated by large compute, but also think about how crucial it is a time to take a responsible stand working in NLP. If you are working in NLP, if you're not, maybe it's a good time to think about working on it and be a responsible researcher there. Cool, thanks for joining this lecture. And thanks for staying with me throughout this lecture that's over 100 minutes long now. This is my contact info. Feel free to get in touch whenever you can.
Thank you so much, Roseanne. That was amazing.
Yeah, thank you.
For students, we have our regular lab at 1, which goes till 3, and then this afternoon, starting at 3:15, we have an AMA with grad students, which includes all of the grad student organizers and possibly a few more people. So if you have any questions about grad school or research as a grad student in general, please stop by. It'll be a regular Zoom meeting, so it'll be more casual. Thank you again, Roseanne. This was really awesome. That was quite a feat to cover that much material. So thank you so much.
Yeah, thank you.
Thank you.
Yeah.
Bye.
Bye-bye, folks. Bye.